There we go. Hey, welcome everyone once again to Astronomy Daily Live. It's 2:01 UTC on the 3rd of June, 2019. Wow, it's already we're already moving into the third day of the month. That's just yeah, this Earth is just spinning really fast. And yeah, like we were talking about last night, um, I think it's sort of a perceptive thing. I think for the most part, time is just sort of plugging along, and sometimes it seems like it's moving really fast, and sometimes it seems like it's moving really slow. Uh, uh, so yeah, I think that's just a perceptive thing. But regardless, it's moving along. Nothing seems to be uh, able to stop it. So, all right, well, here we go. So, welcome. Hope everybody's doing well out there in the universe and the world. Looking at the chat, Carolina Sky Astronomy. Hey, nice to see you. Chuck, also in the chat, has his consumable of choice. I also do. This is the hydrogen hydroxide again, HOH, a nice balanced molecule. So cheers. Tom, hey, nice to see you there too. All right. Yep, everything's good here. So, Bobby on the panel. Hey, what's going on?
Nothing much. Cause man, I thought you was gonna be late and stuff.
Yeah, I was just moving a little slow, and you know, like I say, I've got this process, and I got that process started a little bit late, um, but I went a little faster than I normally did, and I caught up more or
Uh,
less. So
did you get the memo about check me out on now?
I did. I did. I saw that over on my Discord server, which I think there's a link to that down in the description, and then we can pop it on the chat as well here momentarily, I would think. All right. Yeah, you know, I don't, I don't have a watch. I don't necessarily like to pay that much attention to what time it is. But so what I do is I sort of minimize uh, my exposure to time. So there are certain uh, uh, events that really require accurate timing. So you know in that case, it's nice to know exactly what time it is. Like here, right? I mean, I definitely don't want to be more than 1 or 2 minutes late because yeah, it's important that when I say that I'm going to be here at a certain time, you know that I actually am. So all right, well, cool. So yeah, I don't like being late. I like being um, uh, just like moments early. Maybe 1 or 2 minutes early. So
Yeah. I
that
mean,
way,
sometimes you hate going to church late. If I'm going to be late for church, you could just say forget it.
Yeah, yeah. Well, you know, that's what I feel about hurrying, right? I mean, if I have to hurry, I'm I'd much rather just not do it if I don't have to. So yeah. All right. Well, cool. Well, hope
Yeah.
everybody's doing well. The sun is setting behind me. You can see the shadow there of my hand. So yeah,
Yeah.
it's
Oh, you
another.
also want to know why we couldn't do our rabbit on Wednesday
Yeah,
or Thursday?
the rabbit looks like it's having some kind of trouble, huh?
Um, or probably got overloaded because probably the #1 trend was that playoff game for the NBA playoff finals.
Oh, okay, okay. Yeah, because I tried it again um, yesterday, I think, and it was having the same problem, exactly the same. So, yeah, I don't know if.
Hey,
If
Erdogan.
the game, uh,
Hey there, Mr. Ert.
Erdogan, right on time.
I
Hey.
don't. I okay. There it goes.
My hat looks better than my hair.
All right, if you say so.
Yeah, yeah, yeah.
I need a haircut. Like
My hangout's delayed for a little bit. I couldn't even see Ron on there, but I could hear him.
I need a
Oh.
haircut like Bobby. So, you got short hair.
There you go.
Yeah.
Yeah, nice and short. Yeah, mine's starting to get a little on the unwieldy side.
Yeah.
So it's.
I got some
going.
clippers. I can come there with the telescope, and I can bring my clippers, and we can do a YouTube video on it. No, you don't like that idea?
I really don't.
I think
Don't
I'm
like
gonna go to Walmart for my haircut.
Right.
There's like a hair salon at the grocery side at my
There you
Walmart.
go.
Just
wow.
walking distance.
Cool.
It's walking distance.
Well, I actually cut my own. I do. I shave my own when I get
Yep.
ready to.
I do too.
It doesn't cost anything.
My mom
Zip it right up.
used to do it before her final days.
Yep.
I really do not like the idea of somebody running their fingers through my hair. It just creeps me out.
I wouldn't run no fingers through the hair. I'd just shave it right off. You wouldn't have to worry about a thing.
It just completely creeps me out.
No fingers needed with mine. I just take the shaver and zip right off.
Yeah.
Hey.
Yep, and that's exactly what I do too.
Yeah. That's it.
Done. It's done.
Done for 6 months. You don't have to worry about it.
Get that Mr. Clean.
Yep.
Yeah.
Absolutely.
I don't worry about the back. I just shave it. So you don't like how straight my hairline is. Too bad. Uh-oh.
Yeah. Here we go. Cheers.
Yeah.
All right. Well, great. Hope everybody's doing well. As I said here, all is good. Nothing exciting to report here.
I don't think I need a haircut soon. What do you think?
Well, you know what?
We can trim it up if you want.
I really think that's got to be a little shorter because it's getting really dangly. You might be able to do one of those. What are those things called? The Jamaican people have those. The really thick hair.
Dreadlocks.
Yeah, dreadlocks. Yeah. So Bobby, at this point, you could probably start some dreadlocks
Um,
because it's pretty darn long.
yeah. Maybe he can dream about that. Thinking about all. I don't think Bobby ever had that long hair to do that.
Oh, when I was going to school, my hair can go like almost like that Tangerine Spencer.
Oh, okay. You have an afro then?
No,
Oh, no.
it's more like a bushy
Oh,
hair
okay.
style.
Just a lot of hair. Okay.
Cool.
And Grateful First usually calls our president the Tangerine Spencer. Loves to troll on him.
So how about in space, Cosmic? Would we grow hair the same?
I just call him fake news.
Yeah.
Cosmic, would we grow hair the same?
I think I'm sure that kind of thing has been studied, and but I don't know. I don't know if there are any conclusions to that or not.
Well, the reason why I ask is that they're talking about on the space station. Who was it that was there for 360 some days? Who was that?
Yeah, that.
And apparently, his body changed went through some kind of small change, like what he shrunk. No, I think he grew, didn't he? He stretched or what? I can't remember now.
Yeah, I forget. I think you're talking about the twin study.
Yeah.
Where we had these two astronauts that were identical twins, and one spent something like 400
held the record.
400 or some days.
Yeah.
There, and at the same time, his twin brother stayed down on Earth, of course.
Yeah.
And they've I think there have been a couple of reports out. I thought that I don't know if they're in the process of writing a book or if a book has been written. Yeah, I forget. I'm not paying as close of an attention as I probably should with that.
Yeah.
But for sure, there
I
are
don't think the nightbot's working. Because it never responds on the
I think there's a couple of things that I can see happening in space. Just as an example, isolation, first of all. So if you're on the moon, or if you're on Mars, or if you're on the space station for any length of time, you are isolated, and so that would change the way you think. You change your perception, as we were talking about, perception of things, and time wise, how fast time travels. They're all kind of fits with what we were talking about the other day.
Yep.
And so I think our perception in space would be a little bit different, and perhaps the environment might change our physical aspects a little bit, but I think our perception, our mental ability to understand where we're at the moment, like, holy cow, I'm on Mars. Where's my house from here, So that kind of thing would be concerning. It would be a worry, more or less. Even if you had all the great equipment, you'd still be worried.
Yeah.
Yeah, and we don't really know how that's going to be until we pretty much do it. Because we can simulate those kinds of things, but and set up like Mars bases and moon bases here on Earth, right? And we can put people into those things, and they can act like they're on Mars, and but there's this little thing in the back of their head, right, that says just outside that wall is, you know,
whatever.
a nice place, a nice environment.
Yeah.
Right.
But now, if you're actually on Mars, though, you're not going to be able to say that. It's like you're going to say, "Holy cow, the Earth is over there."
Right.
What am I going to do?
And so that little thing that is, giving you some comfort, knowing that you're really, simulating all of this, right? But I really think the only way that we're going to know what's going to happen is to go do it. And
well, I'll tell you what. You go ahead.
We're going to have to see what happens.
You go for it. I'll stay here for the report, and I'll take the report when you send it back.
But as crazy as that sounds, somebody's going to do it.
Yeah. And someone will have to be here to take that report.
Absolutely.
I'm your guy right here. Earth Radio will take care of it.
So am I.
Now, of course, you got to take the radio up there so that Earth Radio can play on planet Mars when you get there.
Very, very true. Yeah. Very, very true. But yeah, I mean, I think they're right when it comes to a lot of these things. We need some infrastructure.
Yeah.
We can't just sort of go there. There's just no point.
Right.
So we have to start building the infrastructure, which is every industry on Earth.
Oh yeah, like Jim said, there's no big D's on Mars.
And yeah.
Yeah, well, not yet.
But the biggest problem that I have is that we don't know enough about planet Earth. We really don't. I mean, with everything that we have on this planet, there is a lot of stuff that we are not even aware of. And my question would be, why not learn here first? And
well, I think that we should do as much as we possibly can. I don't think that there has to be a first and a second and a third and a fourth. No. I think that we should do all of it, every single bit of it. Really, the only thing that is stopping us is the will to do it.
Mm-hmm.
That's it. Because once you start monetizing resources in space, you'll have more money than what you could possibly do anything with. It is.
But they have to get 10,000 subscribers first.
Except that. if they can hit that one, they are smooth sailing.
I think they probably have more than 10,000 actually.
Yeah.
So I think they're good on that.
Right. Well, cool. One of the things that I wanted to do, and I like to do at the beginning of every month also, is look at the solar system situation. Just sort of see where all the planets are, where we are on Earth here in relation to all the planets right now. So one place that you can find that is over at Heavens Above. And so I've already...
Now we're going into summer, correct? Now, are all the other planets going into summer as well? Or is it Earth?
Yeah, no. The seasons are different on all the planets.
Okay. That's good to know.
Uh, Mars, Mars and Saturn and Earth all sort of have the same axial tilt.
Uh,
So they sort of experience the same kind of seasons, but of course, because of their distances
yeah.
To the sun,
It's
they
kind of
are
like
different.
here in some places on the earth. Of course, we got the four traditional seasons, but some parts of the world just only experience two types of seasons, which is the dry season and the wet season.
Yeah, and that is sort of basically what my experience here is that it's dry and then it's wet and then
We
it's
got
dry.
one season here in Minnesota. We got one season, winter.
Yeah,
Yeah.
yeah,
I know you feel sad for that.
yeah. That's awful. All right, here
Oh,
I'm gonna
going into the
share my screen. There we go. So here,
wormhole. There we go.
yeah, here we go. So here is heavens above, and here's where we are um, on June 3rd at 1 hour UTC. We can actually go back to if we want, like that. Hey Bobby, could you turn that down just a little tiny bit,
Not
please?
me. I think that's Ron.
No, it's
All right.
not me. Or is it? Maybe it is me. Okay, I got TV muted. That was TV. Sorry.
Yeah, no worries. No worries. All right, so here we are. So here's the sun. It's a yellow ball here. And now these orbits are all to scale. The size of the planets are not. So they're just all the same size.
You wouldn't be able to put it on the screen if it was.
Yeah, you really wouldn't be able to see them, right? So, but these orbits are to scale. And you can see, that this isn't exactly in the middle, right? It's a little offset here. Venus is pretty round. Earth is pretty round. Mars is a little bit off, as you can see. Well, okay, yeah. So here's Mercury. Here's Venus. Here's Earth. Here's Mars. And so, standing on Earth and looking at the sun, you'll see that Mercury and Mars are to the left of the sun, right? We're looking down on the solar system here. So everything is rotating counterclockwise. So, yeah, so here's uh, um, Mercury and Mars are to the left, which means to the east of the sun. So these are both Mercury is just starting to become visible in the evening sky, and Mars is over there still too for a little while. And then Venus is up in the morning. It's to the right of the sun, which means it's to the west.
So if I seen it, if it was a clear sky, it would almost look like an airplane landing, practically.
It's pretty bright.
Yeah.
They probably actually, did they give us the magnitude here? They don't give us a magnitude, but Venus is probably going to be pretty close to magnitude, like -4 or so. So pretty bright, really, really easy to see. If you get up in the morning, look east, you'll see it. It'll be a big bright thing.
Okay.
Right, so that's how that is. So that's sort of what's called the inner solar system. And then here's the outer solar system, where we've got Jupiter, and as you can see, really, really, really close to the time of the opposition. So, Earth, or Sun, Earth, and Jupiter are pretty close to being lined up now. Saturn is over here. So here's Uranus, and here's Neptune, and here's Pluto. Again, all of these, from Earth's point of view,
Mm-hmm.
are to the west of the sun. So all these guys, that one, that one, that one, and Venus are all in the morning sky. Jupiter is pretty much up all night long now. And then Mars and Mercury are up in the evening. So that's what it looks like from above. Pretty exciting. Here's the distances. So, and velocities and stuff. So you can sort of see that right now, Mercury is about a third of an astronomical unit from the sun, but 1.2 astronomical units from the Earth. Right. So, yeah, and that sort of makes sense. 1 astronomical unit is the distance between the sun and the Earth. So this is 1, and then 0.2, about a fifth of that. Yeah, I think that's about right. So cool.
Well, there's always. I have to go though, so I just wanted to stop in and say hello.
All right. Well, thanks for coming in, Ron.
All right. Yeah, we got
you.
some.
Later, Ron.
Got a music project I gotta be at, so.
Excellent.
We'll see you next time. All right. Thank you again.
Okay, okay.
Bye.
Bye-bye.
See you later, Ron. Yep. Bye. So let's see what else is this showing here. So as you can see, the closer in the planet is, faster it moves. So Mercury is moving pretty fast, almost 55 kilometers per second, almost twice as fast as the Earth is. But the Earth is really moving too, 30 kilometers per second. Do you feel anything? I don't feel anything.
Not me.
But that's our orbital motion. So that's how fast we're moving as we go around, right?
How can we be moving so fast that we don't feel it?
I don't know. I have absolutely no idea at all. The only explanation that I've ever heard is that it's super, super, super smooth, and we're really used to it. So, it's sort of like fish probably don't know that they're in water, right? And so, maybe it's the same thing with us. We just don't know. Anyway, yeah. We're just moving incredibly fast.
All right, Tom Van Scar said everything around you is moving at the same speed.
Yeah, well, that's true. So, everything looks like it's stationary because relative to you, everything is. But yeah, I mean, it's just a relative thing. That's and that's actually one of the things that they leave out here is, you know, what is this velocity relative to? Is it relative to? Yeah, it's probably some kind of heliocentric thing. So, you know, it probably has to do with uh, uh, relative to some position in the sun is my guess. But yeah, I'm not exactly sure about that. Anyway, as you can see, they move out, move out. Yeah, pretty interesting. So anyway, that is the situation with the solar system at least as of right now. And you know, over the course of a month, lots of things change. Um, Over the course of 30 days, that's about 1/3 of an orbit of Mercury. So in a month, Mercury will be, you know, like way over here. Venus is something, I think of Venus here is something like 144 days. So that's about, oh, is that right? Yeah. Anyway, so yeah, there is the situation with the solar system. Very cool.
And it's sad we can't live on Mercury and Venus, but we can definitely live on Mars.
Mm, yeah, I don't know about that. I don't know. We we've got to just give it a try, see what happens. Um, Probably some of it is not going to be very pretty at all. So yeah, it's not going to be nice. But I think at least a lot of it will be. At least I hope so. All right, well, cool. So there's a couple of directions we can go. There's always way too many directions to go.
And we're going to say hello to Andy, Callie, and Jim is going to be leaving us.
Okay, very good, Andy. Nice to see you. Jim, stop in any time you want. Spend as much or as little time as you want to. Of course, you're always welcome. So, yeah, and you've got your priorities right. Okay, if it's clear and it looks like it's gonna, you know, be some good shooting, go. Absolutely.
Symmetry.
All right, cool. So yeah, always lots of options. We can stick with Aries. We were and it's been a little while, but we were sort of slowly moving through uh, various objects in the constellation of Aries. We can, why don't we just go ahead and continue that? Let me pull this up here. And then we can sort of using Wikipedia as a bouncing off point. So let me get down to the objects themselves. So I think we were looking at a couple of variable stars.
whenever I was going to school, Wikipedia was starting to be a thing. But we can't use Wikipedia. We got to use the database center that the school gave us.
Well, that's uh, yeah. They probably want to ensure that kids are getting accurate
Yeah.
information.
I
So
I think one day they're just gonna filter Wikipedia and they can do that too.
yeah, who knows? Who
So
knows?
on this day in 1966, Surveyor 1 soft landed on the moon. It was the first American space probe to land on any extraterrestrial body. It had more than 100 engineering sensors on board. However, its last contact with Surveyor 1 was on January 7, 1967.
Very cool. Yeah, so that Surveyor 1 was first American space probe. Wow. Very, very cool. On this day, 1966. Pretty amazing. More than 100 engineering sensors. Wow. Very interesting. I guess that means soft landing. I would think so. Yeah. Yeah. And Tom, encyclopedia was my thing too. In fact, I spent many weekends um, going to the main library downtown and going through these big thick books that are called the Reader's Guide to Periodical Literature, and it's just an index of all the magazine articles, and it was basically Google, right? I mean, what Google is now is, well, much more than what this thing was or is, but pretty darn close, pretty close. Anyway, so let's see. I think I've got the Wikipedia page for Aries. So let me share my screen again, and we will keep investigating Aries here for a little while. See what can be seen. So I think we took a look at SX, Aritus. I don't know if we looked at that with Simbad. Why don't we find out? Basic search, SX, Aritus. I don't think so. So obviously also known as 56 Ari. Let's see. Yeah, it says it's a variable star. Very prominent emission lines of helium-1 and silicon-3. Which, at least in terms of, I think, the helium, I think that's a little unusual. That's a little weird. So makes the star, I guess, a little bit more interesting. Let's see what we've got here. Pretty bright, just sort of on the edge of human visibility. What 6th magnitude or so, something like that. Probably a picture of it here for what it's worth. Not much to see there, but we can look anyway. Let's see if that shows it off any better. Yeah, kind of hard to tell. Nice picture though. Yeah, it's not coming up too well here. Okay, well, let's keep going with that. Scooch on down over here. So this is a variable star that is of a particular variable star type. So every, I mean, we humans like to classify things. So we've classified variable stars into different types, and usually those types are signified by whatever the name of the discovered star is to have these new characteristics. So I guess in this case, 56 Ari, otherwise known as SX Ari, is a variable star that is of type Alpha 2 Canis Venatici. So yeah, we'll have to investigate a little bit what that is, and we should be able to find that out. So here's a bunch of different names for that same star. So SX 56, HD number, sort of the usual players. They even have Gaia data release 2 in here, so that's pretty cool. Let's see. Wow, so lots of references. It's kind of interesting. I sort of correlate, I guess, lots of references with maybe it's kind of interesting. So this has quite a few, so maybe sort of interesting. I don't know. Looks like there's lots of measurements here, including a distance, a diameter. Wow. Let's see here. So these folks, not quite sure what that is. That might be Gaia. Are putting it at 124 parsecs. So let's see, I gotta grab my handy dandy calculator, which is still working. I'll have you know.
So it's coming from IRAS, IRC, SAO, and CLG, or ACO. The GJ has been removed.
Oh, okay. All right.
Yeah, look at the warning label.
Yeah, I see that. All right, so a parsec, PC there, is 3.26 light years. So then we can multiply that by 124.358. And we get 405.4 light years away. So that's, as far as stars go, yeah, that's sort of middle of the road. Yeah, it's not really close. It's not really far. So this is kind of interesting. They actually measured the diameter of this star. Got 7 7.35 million kilometers. Pretty neat. I never remember the diameter of our sun. Let's go over here and remind myself what the diameter of the sun is. Distance. So equatorial radius is something like really, really close to 700,000 kilometers. So that means the diameter is 1.4 million kilometers. Okay, so our sun is 1.4 million kilometers. This one is 7.35 million kilometers. So it's about 7 times as big as our sun, at least according to these folks. And I'm kind of curious to know where they came up with that. I think we've looked at this kind of thing before in some previous live streams, and these diameters sort of pop out of models. So I'm wondering if this is the same thing. Let's find out. So let's go over to the ADS here. Gulp down some of this HOH. Excellent. Taking a little while to load here. That either my internet is slow or it's a very long paper.
Probably just a long freaking paper. Well, paper.
Yeah, it's only 18 pages, so slow internet. Okay, so let's see. These folks are doing what? So this was back in. Okay, it says this was printed in 2018, but I'm seeing 2014 here, so I'm not quite sure when this was done. So that's kind of a bummer.
It's typo in the calendar in the paper.
What's that?
Probably a typo in the paper.
Yeah, who knows? It's it's impossible to know for sure. So let's see here if we can figure out. We might just try finding our star first. But let's go through here and see. It's kind of some really bizarre looking images here. Don't know what that's all about. Yeah, these are a little strange. Not quite sure what those are. So these look like spectra of some sort. Visibility as a function of wavelength. Okay, yeah, so these are all models, spectral models of some sort. I am not quite sure what they're doing here. Let's see. There's a spectral line of some sort, an absorption line. Closure phases as a function of wavelength. I just wanted to Okay, so here is, this is probably where we're seeing that, my guess. It's probably an HD number 19832. Yeah, there it is. So that's why that is referenced here, I guess. Yeah, because they give a radius in solar radii. So yeah, actually here they're saying 5.28. Does that match? I guess so, right? Because these guys said about 1.4. Yeah, so I think that's about right. 5.28 times the radius of our sun. Very cool. Wow. So, all right, well, that's why that's there. 19832. I don't know if we can find that or not. 192. Oh, that's the only one. Okay. Well, cool. All right, well, that's why that's there, obviously. And it came from a model. Came from a model. All right, so some velocities all look relatively consistent, spread out in time quite a bit. Wow, 1915. Proper motion, except for this one back in 1971, they all look about the same. PLX is parallax, which is an indication of distance. I guess this is the spectral type. So it looks like they sort of nailed that down pretty early on, that it was a variable star, sort of a weird one. Okay. All right. Well, let's dive into these papers a little bit and see if we can determine what's so interesting about this guy. Oh, what was his number again? HD number 19832. I don't see it there. Let's see. I'm trying to think about what to search for here. Maybe just airy. Let's see what that does for us. So there is 50. Okay, so that's it. So this is talking about the Lorentz force in atmospheres of chemically peculiar stars. I don't remember what the Lorentz force is. Let's dive a little into this and just. So I don't remember. Okay, so the Lorentz force is the result of the interaction between the magnetic field and the induced currents. Okay. Modifies the atmospheric structure and induces characteristic rotational variability of pressure-sensitive spectroscopic features. Okay. All right. Lorentz force is a is an electromagnetic um, force that I guess they're trying trying to explain or use to explain the behavior of this star. Let's sort of see what this goes. Take another gulp of this nice stuff. That loaded nice and fast. So the atmospheres of magnetic, chemically peculiar stars display presence of global magnetic fields ranging in strength from a few hundred Gauss um, up to several tens of kilogauss. Lower order multipolar components. Okay, so coming back up here, looking at the abstract, see, in this work, we continue the presentation of results of the magnetic pressure studies in MCP stars, which are these magnetic, chemically peculiar stars, focusing on the high resolution spectroscopic observations of the BP star 56A. Significant variability in the hydrogen lines. So these guys are seeing hydrogen lines. Okay. I thought this was talking about the fact that it had very prominent helium lines. Let's see. Probably not going to be able to get too much into this either. That's all right. So they actually made observations of this object. That's cool. So these spectrographs, the shell spectrograph is a very, very high resolution spectrograph. Yeah, you can see extreme details. Yeah, they're pretty amazing. Looks like they use a nice size scope. Wow, over in Korea. I didn't even notice who the authors were. Okay, cool. So they're sort of all over the place. Austria, Sweden, Mexico, Korea, and Russia. Wow. But it looks like the scope that they used was over in Korea. Cool. Let's see, what else do we got here? So here are the abundances. So yeah, this is kind of a weird scale. It's a logarithmic scale. Bobby, that's getting a little bit loud. Is there a chance you can turn that down? Just a wee bit, please.
I turned it off.
Oh, well, thank you. I appreciate that. So yeah, this is just showing, and it's kind of nice. I'm sort of glad that they also show the abundances of the sun. So you can sort of see how um, the um, the abundances of helium, magnesium, aluminum, silicon, and iron um, are different in 56 Area than they are in the sun. Now, hmm, man, I would have to think about that. I think the if this number is more negative than this number, then I think this abundance is actually higher. I think it's a negative logarithm, so it gets really complicated. Yeah. Anyway, for sure there are differences between our sun and this star in almost every way, for sure. That's kind of interesting. Oh wow! So here's a. Let's see. Is this showing any? I don't know if this is showing any actual data or if this is all just models. Comparison of the observed and computed spectral energy distributions, which is just a fancy way of saying a spectrum. So yeah, I'm not quite sure. These, yeah, these lines here. See these absorptions here. These are the hydrogen lines. So here's hydrogen alpha. Here's hydrogen beta. Here's hydrogen gamma, delta. It goes all the way down to sort of a magic number. But yeah, I don't know if we're seeing spectra there, spectral lines from actual data, or if we're seeing something out of a model. Not quite sure. But cool, no matter what. Line profiles. Spectroscopy is just a crazy, crazy, crazy thing. Wow, lots of lots of conclusions. Wow, lots of residual spectra. Holy moly! Yep, they looked at a lot of these things. Pretty cool. Not quite sure, not able to completely follow this. It's flying way over my head, but it's a little interesting. Seems to be sort of a kind of an unusual star. Pretty cool. Let's see. Go all the way back here. See if we can find another one. It's going to find all the ARIs. Okay, so here's one. So ultraviolet variability of the magnetic chemically peculiar star 56 Auritus. So this is looking at it in the ultraviolet and seeing variations in its brightness. So wow, it's just it's varying in brightness all over the place. That's pretty cool. Let me do this a different way. I'm going to, nope, need to do that. We'll find it again here. There it is. So we'll do this instead. So far ultraviolet. Okay, cool. So they used a data from the International Ultraviolet Explorer (IUE), which is a spacecraft that I don't think is in operation anymore. It looks like they used like archived data. Yeah. So this study is based on the archival IUE data obtained at different phases of the rotational cycle. Cool. Neat. Let's see. See if we can find an ultraviolet spectrum. I don't know what the capabilities of IUE were. But yeah, as far as I know, and it might actually say here if IUE is still operational or not. Yeah, maybe not. So here they're talking about the star itself. IUE spectra. Following list of a series of 3 observations of 56 Area obtained with the SWP camera was received from the final IUE archive. Okay, well that doesn't help me much, but we will press on here. So period variations. Not too surprised at that. There was a increase in the rotational period, 4 seconds every century. So that's, that seems sort of insignificant, right? 4 seconds in 100 years. But it's those subtle differences that allow us to, find hidden planets, or find out something interesting about the star that is exhibiting this kind of weird behavior. So it's nice that we have looked at it enough to be able to notice that its rotational period is changing. And then the question is, well, why? And I think that's one of the reasons why this star is a little bit interesting. So yeah, just on and on and on with that. They're showing. So these are so-called phase diagrams. These are showing a rotational phase. So going from 0 to 1 would be going around once. So one rotation goes from 0 to 1. So and then that is plotted up against brightness, or what they're calling flux. And it looks like it's at 2 different wavelengths, right? So 2 different ultraviolet wavelengths. and yeah, it's got an interesting interesting light curve, interesting shape. Um, the the data here looks pretty good. You know, it's I find it comforting to see, you know, error bars and whatnot. So it's nice to see those. Um, so okay, yeah. So these are just different sets of observations, and that's why there are some that are um, open circles, and some of them are filled circles, and some of them are squares. So those are just the different observation times. And yeah, looks good. Looks like they got, you know, some pretty decent data. The fit, which is what this other line is, the solid line through here, is a fit that was created by a model where you have, you know, all these different parameters that you can make adjustments to, you know, to make this nice fitted curve. So, you know, could those parameters all be completely wrong and you get exactly the same curve? Sure, absolutely. But you know, after a while, you collect a lot of data, you run it through, you check your model, you know, all that. You get pretty confident with models after a while. Hopefully, never 100%, but yeah, you know, after a while, the models uh, are pretty reliable, I guess. So, but yeah, you know, that's a nice fit for sure. Okay, so here's a little bit of spectrum going from what about, well, just below 1200 angstroms all the way up to 2000 angstroms, and they're identifying some elements there: silicon, carbon, Cr. What's Cr? Is that chromium? Wow, I don't know what Cr is. Silicon, carbon, aluminum, iron. So that's what they're saying, that these absorption features are. See how these sort of dip down here and then down, and then see here's this one and here's this one. See how they line up with these, and sometimes it's sort of a double line that you can't really see all that well. So yeah, you know, this is for me a little hard to swallow because you know, it's like, you know, this this looks like a noisy wiggle, yet they think that they've identified things in here. So yeah, I don't know. Maybe that's just the skeptic in me. What's this here? So phase diagrams. Oh, okay. So looking at different wavelengths, that's pretty cool. It's kind of interesting. Um, is this for the? Yeah. So this is looking at a bunch of different wavelengths, and you can see how the star not only varies in time, which is what this axis is, right? It's phase, rotational phase, um, but it also varies in terms of wavelength. So that's pretty cool, pretty interesting. It's like, you know, 1213 here hardly changes at all, while 1254 has this huge variation here. So 1254. Maybe that's, you know, to do like silicon or something. 54. Yeah. Maybe around here. 1213. I'm not quite sure which one that is. 1502. That's up here somewhere. Maybe a silicon again. So yeah, you know, it's really, really interesting what you can see with these things, and see how, you know, if you look at this in different ways, it looks you know, radically different. Same star, same everything. Pretty cool. Okay, so here's another spectrum. Cool. So for 3 phases, I don't know if I'm seeing 3 phases here. The solid line shows the difference between phases, 0 and 0.25. So the phase has to do with the rotation of the object, right? So they're looking here between 0 and 0.25. So the first quarter of the rotation. So the solid line is looking at the difference between those two as a function of wavelength. Wow. So yeah, that's kind of interesting, right? That's like a difference spectrum. So yeah, I would have to think about that a little bit to really, really understand it. But it's pretty cool. I never thought of doing that, of looking at the difference in spectrum like that, you know, during different times. Kind of cool. Okay. More wiggly lines here. See what else we got. Okay. Again, probably much more than what I want to get into. Pretty cool, though. All right. Well, I think I'm looking at the clock, and I'm thinking that it's about time to get on out of here for today. So I'm going to stop sharing, and I'm going to do that, and I'm going to look at the chat really, really quick. Make sure that there isn't any major shenanigans going on there. Doesn't look like there is. Excellent. Excellent. All right, everybody. Well, I think I am going to get out of here for now. So take care. Peace, cheers, and all that. More astronomy talk tomorrow, and practically every day. 2 hours UTC. So make sure to subscribe. If you haven't, hit the thumbs up if you so desire. Spread the word. Share around. Yeah, this is just a fun gathering each and every day. We talk astronomy, space, science, all kinds of nerdy things. And, you know, just have a good old time. for about an hour. It usually goes a little bit over an hour, as you can see. So, but right about now, it is time to get on out of here. So, all right, everybody, take care. Peace, cheers, and all that. Live long and prosper. And I will see you on the spin. Just one spin.
All right. Hey, by the way, you're gonna be looking at Check Me Out it will soon.
I might. I might pop over there. Maybe. We'll see.
Yeah.
We'll
All
see.
right.
All right. We'll see you later, everybody.